Hi everyone, my name is Olga and I'm from Queensland University of Technology in Australia. Thank you for inviting me to give a talk at the workshop and thank you for the opportunity to present my work. I would really like to attend the workshop in person, but unfortunately I won't be able to do so. My main interest is deep learning for animal identification, and today I'm going to present the details of my paper, Learning Landmark Guided Embeddings for Animal Identification, written with my co-authors and supervisors, Ferraz, Frederick and Massa. My main interest is identification of marine animals such as manta rays, humpback whales, dolphins that have unique markings on their bodies. These animals are vulnerable and of huge interest for marine biologists in Australia. I'll start with background and motivation behind my research. Then I'll discuss proposed method and the datasets used for experiments. Then we'll have a look at the results of these experiments. And finally, I'll discuss possible future work. Let's begin with some background behind my research. Some animals have unique markings on their bodies that are unique for each individual animal and act like human fingerprints. So biologists use these photos to identify sightings of each particular individual and record it in a database. So it happens that this photo identification is an effective non-invasive tool to track movements and connectivity, to investigate habitat use and population size. So, for example, manta rays have unique markings on their bellies that stay the same throughout the animal's life. Humpback whales have unique shape of their tail and unique coloring pattern. And right whales have unique callosity pattern on their head. Primary focus of my work is re-identification of manta rays. But why do we need to recognize them? We collaborate with Project Manta from University of Queensland to obtain the photos and get some additional knowledge. Manta rays are actually really important for ecotourism and fisheries industries. For ecotourism, it's important because tourist operators can offer reliable wild encounters due to interactive nature of these animals and their predictable aggregations. And for fisheries, manta rays are targeted by commercial and artisan fisheries for their highly valued gill rakers to use in traditional Chinese medicine. These factors have resulted in manta rays being listed as vulnerable to extinction. And photo ID databases have proven a very useful tool for assessing population sizes, connectivity, and movement. Currently, in Asia-Pacific region, marine biologists do the identification manually because current software have constraints on image qualities and pose of animal in the image. This is especially true for images coming from citizen scientists. They're really hard to identify with the current software. The marine biologists have decision trees that help them to narrow down the list of possible matches for visual inspection. To visualize how hard it is to find a match, I propose a little exercise to find a match in manta rays to a query image. So which one is matching 1, 2, 3 or 4? I understand that it will be easier with an option of zooming in and change illumination, but if we look at this, we get an idea that it's not an easy task. And the correct answer is number 1. To give you an idea about the diversity of images in manta ray dataset, here are some challenging examples. There is variations in viewing angles, and from some angles it's not even possible to identify the correct individual. There is also poor visibility underwater, so some images are really blurry, and challenging illumination conditions make it harder to identify an animal, and occlusions are present in front of the belly pattern in form of small fish and water bubbles. So let's summarize what are the challenges in photo identification of wild animals. First of all, there is a diversity in data. As we see, many of photos are provided by citizen scientists. There is a huge variation in image quality and poses of animals in the images. Then there is the size of the dataset. There is a large number of individuals, like over thousands of different animals, and there is a small number of images per individuals. In many cases it can be 10 or less. And overall the size of the dataset doesn't exceed a couple of thousands. So it's really hard to use deep learning methods on this data. And finally, the variations in natural markings between individuals is really subtle. So there is much more ambiguity when identifying individuals by their markings than when identifying people. To summarize, my goal is to develop a robust re-identification method using deep learning to overcome these challenges. And I believe that these challenges are applicable not only for manta rays, but for other ecological datasets of animal identities, including whales, tigers, and zebras. In my current work, I look into methods to distinguish between individuals with subtle variations in their markings. Re-identification models developed for people recognition learns embeddings for images of people's appearances in such a way that the distance between embeddings of the same person is smaller than the distance between embeddings of different people. However, visual animal identification is mainly based on body markings, which are more ambiguous than a person's appearance because of similarities among different individuals. For example, different manta rays can have a very similar spot pattern, but located at different positions on a belly. The figure shows how two manta rays with only one black dot on the belly, and the only difference is the location of the spot with respect to the landmarks. And the landmarks here can be eyes, gills, and tail. We propose to improve embedding learning for animal identification by explicitly adding locations of body landmarks to the model input. The new model will receive information about the position of distinctive features with respect to the body. So now I want to highlight the key contributions of our work. At first, we propose a novel method to exploit body landmark locations to improve the performance of re-identification system. We also introduce a heatmap augmentation method to train model to handle missing or not visible landmarks. And finally, we show the robustness to uncertainty in body landmark coordinates, and that our model can handle errors up to 10% of the image size. Before going into details of the proposed model, I'd like to highlight limitations of transferring face and person re-identification methods to animal re-identification. At first, faces are usually normalized to an upright frontal pose thanks to robust method to detect facial landmarks, and body postures are aligned vertically. Warping to a canonical position or alignment is not always possible for animals due to sensitivity of these methods to errors in coordinates of body landmarks. And finally, wildlife datasets have limited data compared to large public datasets for face and person re-identification. So there is less chance to learn the relation between the body landmarks and unit markings from the data itself. Moving on to the details of the proposed model. As a baseline re-identification model, we use one of the best models developed for person re-identification that is generic enough to be transferred from people to animals. The backbone of the baseline model is ResNet50, and it outputs re-identification features and class scores. The baseline model is optimized with a weighted combination of three losses: the smooth cross-entropy loss over training classes, the triplet loss, and the center loss. We propose to add the body landmark information to the model input by concatenating extra channels with 3 RGB image channels. These additional channels guide feature extraction to learn embeddings that are aware of the location of distinctive features with respect to body parts. The model is encouraged to use landmark information by learning auxiliary reconstruction tasks on input heat maps from embeddings. We favor heat maps over exact coordinates to encode the estimated body landmark location because heat maps can represent uncertainty. We call this model landmark ID model. Information about landmarks can be obtained from any model that predicts landmarks based on the image, and this is out of scope of my current work. And landmarks can also be annotated manually. Our model is optimized with the combination of re-identification model from the baseline model and the heat map reconstruction loss, which is a binary cross-entropy loss. The next important aspect is two augmentation techniques for heat maps to improve the generalization ability of our model: noisy landmark augmentation (NLA) and missing landmark augmentation (MLA). We introduce these augmentation techniques for two reasons. At first, locations of body landmarks cannot always be annotated correctly, especially when these are obtained from an automated landmark detection model. Secondly, due to large variations in animal poses, some landmarks may not be visible in the image. Our augmentation technique addresses these two problems. NLA randomly shifts the blob in each heat map by a number of pixels less or equal the radius of the blob. And this way the landmark location is still contained within a blob, but not always in the middle. MLA replicates a missing landmark and randomly sets the corresponding heat maps to all zeros. Now I'll discuss the datasets used in the experiments. We verify ideas on a synthetic dataset first, as it gives the ability to control the number and variety of examples. Then we test on the dataset of real images of manta rays. The design of synthetic images is inspired by manta rays' belly patterns, but doesn't aim to replicate it. Each row shows a seed pattern and three generated examples for one identity. An identity is a unique pattern of ellipses. Examples belonging to this identity are generated by applying random projective transformations to the seed pattern and adding a random background. The corners of the triangle where the pattern is located play the role of body landmarks. On the right, there are examples of 3 identities from a manta ray dataset. Each row shows 4 examples for one identity. Images are manually annotated with 5 most distinctive landmarks: right eye, left eye, outer corner of the 5th right gill, outer corner of the 5th left gill, and tail. Due to large pose variations, only around half of the images have all 5 landmarks visible, 30% of the images have 4 visible landmarks, and the rest have 3 and less visible landmarks. Colored points represent locations of the landmarks and are plotted over images for illustration only and doesn't appear on images itself. Let's look at the results of the experiments. The landmark ID model is trained in two stages. At the first stage, only randomly initialized weights of backbone ResNet 50 model are trained. In the second stage, the heat map reconstruction block is trained. Experiments demonstrate that landmark ID model outperforms the baseline model on both synthetic and real datasets. This demonstrates that additional pose information is beneficial for learning discriminative embeddings. Landmark ID model reaches 89% top 1 accuracy versus 63% top 1 accuracy of baseline model on the synthetic data. The real data is more challenging. Baseline model demonstrates 44% top 1 accuracy, while landmark ID model goes up to 62%. To summarize, I demonstrated today that additional input of body landmarks improve learning of discriminative embeddings. In the future, we will conduct experiments on other real datasets, such as tigers and elephants, and explore other ways to exploit landmark information for identification. We also plan to investigate how to train an accurate body landmark predictor on a small dataset and integrate it with the re-identification model. Thank you for your attention. I'm really glad to share my work. I'm sorry again for not being able to present in person and answer the questions. All questions are welcome at my email. Thank you. Bye.